All right, welcome to the online causal inference seminar. Today we have a talk by Jessica Young from Harvard University on causal inference with competing events. We'll look forward to that very much. In the Q&A during the talk, we actually have Mats Tansrud from EPFL, so feel free to submit questions, as many questions as you like. Our discussant today will be Jacqueline Rudolph from Johns Hopkins University. So she will give a short talk after Jessica, and we look forward to that as well. I will now switch over to Yang, who will describe the Q&A process, and then we'll get going.
Thank you, Emma. So as usual, please submit your questions whenever you have it in the Q&A section. If you haven't used it before, it is just a button in the bottom of the Zoom window. So please do submit the questions using the Q&A instead of the chat for us to better track them. And I think today we'll try to save the questions for Matt and also for Jessica to the end of the talk. But if you do have some clarification questions, please feel free to bring them up. Without further ado, please feel free to get started, Jessica.
Thank you.
All right, you should be able to share.
Okay. Can you see?
Yes.
Full screen and moving slides?
It's moving, yes.
All right, awesome. Okay, thanks very much for the invitation. I'm going to be talking about causal inference with competing events. But first, what is a competing event? In failure time settings, a competing event or a competing risk is any event that makes it subsequently impossible for an event of interest to the investigator to occur. So inherent to the definition of a competing event is what is of interest to the investigator. As a running example that we're going to use throughout, in an early trial, investigators were interested in an effect of estrogen therapy versus placebo, specifically on prostate cancer death in men recently diagnosed with prostate cancer, but some men in both of the study arms died of other causes, for example, due to cardiovascular events. So in this example, death due to, say, cardiovascular events are competing events for the event of interest, death due to prostate cancer, because obviously an individual is deterministically prevented from dying of prostate cancer once he's died of something else. And importantly, competing events can occur regardless of study design, for example, whether or not the treatment is randomized. So there are several different measures that have been defined and widely popularized in the survival analysis literature, ostensibly as the basis for quantifying associations between, say, a treatment or exposure and an event of interest, subject to competing events in the sense that I defined on the previous slide, meaning there exist events that prevent the event of interest to the investigator from happening deterministically. And these popular measures include the cause-specific, cumulative incidence or crude risk, the marginal cumulative incidence or net risk, and the cause-specific and subdistribution hazards. And these measures, you can find descriptions of them compared and contrasted in many, many textbooks and many papers. And I think it's safe to say that the vast majority of applications with competing risk data, whether we're talking about trials or observational studies, and the goal is in some sense causal, meaning there is either implicitly or explicitly interest in a causal treatment effect. Most studies use statistical methods that were in some sense derived from starting off with contrasts in one of these measures. And as I'm going to talk about, probably the vast majority focus on the cause-specific hazard. However, even in a trial where the treatment is randomized, and even if everything else about the trial is, quote, perfect, whether any of these associations can be interpreted as causal treatment effects at all, and even if so, which effects in particular they quantify, are not straightforward questions to answer. And while many, many authors over the last decades have made fairly decisive recommendations for choosing between these quantities in terms of targeting a causal effect, these recommendations, I would say, have not been typically explicitly grounded in transparent reasoning around causality, meaning there's no stated counterfactual target and there's no explicit causal model to help with reasoning around both interpretation as well as identification. And it turns out that when we do sort of ground our thinking in an explicit counterfactual causal model, we can see that even contrasting counterfactual versions of any of these sort of typical targets, for example, had everyone received estrogen versus had everyone received placebo, may not actually coincide with a causal effect at all, but beyond that, the investigators' desired causal effect that may or may not have been explicitly articulated. And I'm going to argue also that the confusion may not be helped by the causal inference literature in the sense that where statistical methods are explicitly grounded in counterfactual notions of causal effects explicitly defined. But again, the existing generic notions of causal effects that we have to choose from when applied to this setting may not, again, coincide with what story the investigator would explicitly tell about what they wish to learn from this study, even in a trial. And so here what we're going to do is consider various counterfactual targets that have been historically posed that come out of both the statistics literature as well as consider some options that we could pull out of the historical causal inference literature, specifically for the case where the investigator is interested in a causal treatment effect on an event of interest subject to competing events. And we're also going to motivate a new class of causal effects that really does come out of stories that investigators have told either in discussion sections or when pressed about what they wish to learn from a study that could be useful options in this situation. So we're going to continue on with this running example of estrogen and prostate cancer. And I'm going to sort of pose a hypothetical scenario, perhaps, which is a situation I find myself in a lot. Say you're the statistician, you're working with investigators, and what you've gleaned so far is that they tell you we're interested in the effect of estrogen therapy versus placebo on death due to prostate cancer. So in some sense, we understand the treatment of interest and the event of interest, and we know we have possibly competing events. They hand you a data set, and let's just to remove all other complications, say this data set is a perfect version of the estrogen therapy trial that I mentioned earlier, in the sense that assume everyone adheres to the treatment they were randomized to for as long as they're alive, or up to the planned study end, the administrative study end, whichever comes first. So let's just for concreteness, suppose that this is 5 years post-randomization. Suppose that no one drops out of the study before its planned end, or loosely, no one is lost to follow-up, which for our practical purposes helps us in that for those who died during that 5-year follow-up, suppose we know the day of death and the exact cause of death. And this just gives sort of a formal notation for that observed data structure. So as usual, we can denote A as the assigned treatment at baseline. Say A equals 1 is estrogen, active treatment, A equals 0 is placebo. And suppose we're able to measure on every subsequent day, which we can index by K, going from 0 up to capital K plus 1, indexing that administrative study end. Suppose on every single day, we're able to know YK, an indicator of whether or not an individual failed due to the event of interest by day K. So in our example, this is just yes, no. Did an individual die due to prostate cancer by day K? And then we know DK, an indicator of whether a competing event was experienced by day K. So for simplicity, let's just assume that the only competing events are deaths due to cardiovascular disease, but we could make DK a vector of as many possible different events as needed. And hopefully by the end, it will be clear how to think about whether we need to pull out different causes or not. And using sort of typical shorthand notation, we'll use an overline for history. So Y over bar K would be the whole vector of the event of interest process history from baseline up to time K. And then we can use an underline for future. So say y underbar k+1 is the whole future process of the event of interest from k+1 up to the administrative study end. So now this was a lot on this slide, but really we can just summarize all of this information simply here. So we know A and we know the whole D bar, Y bar vector from 0 to the end of follow-up capital K+1. So I just want to quickly switch over to for those of you who are familiar with sort of the quote classical competing risk literature, say you've read the famous Fine and Gray paper, the way I've described the data structure here is a little different than the way you would see it in one of those papers. So there you might see, for example, instead of A and the Y bar, D bar history, you might see A and a T tilde, a min of a failure time, and comparably an administrative censoring time, as well as an index of the quote cause of failure, say due to prostate cancer or due to cardiovascular disease, where T is just time to first failure from any cause. So this is like a time to all cause mortality in our case, and C would be just 5 years for everyone. J = 0 for an individual who never fails through the administrative study end, and then J = 1 for one cause, J = 2, and so on. So this way of defining the data structure is consistent with the way that we defined it on the previous slide, in the sense that if I know this, then I know this whole event process. The reason that we're going to define it this way, what I call a less summarized way without sort of thinking about a T, is that it more transparently acknowledges the time-varying nature of relevant event processes in this problem, which, as we'll see, is relatively crucial for transparency around interpreting different counterfactual targets, as well as for identification. And this talk is going to be mostly focused on posing different estimands and their interpretation, but I will allude a little bit to practical issues around identification as well. So the key feature of this data structure that makes it effectively a competing events data structure is the fact that if an individual is known to experience the competing event by, say, a particular time index K without having failed of the event of interest, then deterministically the whole Y future will, by definition, be deterministically 0. So this is just a feature of the factual world. This future is not missing, it's just deterministically 0. This is just what happens. When you die of a heart attack, you cannot subsequently die of prostate cancer. So now that we understand the data structure we have, let's go back to the causal question, to at least to the degree that in our hypothetical scenario it was articulated so far. So all we know is that the investigators are interested in the effectively the effect of A on Y at by some time K. And there are many, many ways to possibly define a causal effect like this. This statement doesn't fully clarify what the investigator's full intent is, what the investigator wishes to learn from this trial. And as we'll see, there's reasons to believe that there are a number of possibilities. So before we go any further, I want to, just like we sort of have a concrete definition of a competing event, I also want to have a concrete definition of what I mean when I say causal effect here, because people can mean different things. What I mean here is a contrast of counterfactual outcome distributions in the same individuals, but under different treatments. And so by restricting to this definition, any contrast that we consider, the only explanation for a difference can be due to the treatment and not to comparing different groups of individuals. So let's start out with thinking about a counterfactual contrast in the sort of well-established cause-specific cumulative incidence, where cause-specific here refers to the cause of failure, not to the treatment as a cause. So just in this discrete sort of time structure, which I do intentionally to sort of keep things simple, because nothing changes about the interpretation here fundamentally, and it just sometimes helps people to understand these concepts better. So a cause-specific cumulative incidence for the cause of failure that the investigators have articulated their interest in this example, prostate cancer death, is simply, we can simply understand it at any particular time as the probability that yk equals 1. That's it. So in our example, this is just the probability of dying due to prostate cancer by a particular time. I indexed here just the last time, but depending on our interest, we could put any time index here. So a counterfactual contrast in this would just be the probability that y equals 1 by a particular time had everyone received estrogen versus, say, had everyone received placebo. So this is a very familiar looking type of causal effect, counterfactual target. It meets our definition of a causal effect because it's comparing outcome distributions under different treatments in the same people. This is referring to the same population. And now I'm going to sort of bring in identification just very briefly. The reason that I refer to this sort of imaginary version of the study as perfect, because under this case, this counterfactual guy is guaranteed effectively identified by simply this contrast in factual, which turn out to be observed probabilities in this case, the probability that y equals 1 among those who actually received active treatment versus among those who received placebo. So this is sort of the classic case of association equals causation. And obviously very simple statistics could be used to estimate this in this case, say just a difference in sample proportions. So why do we have so many options in the competing risk literature? Why, for example, are the vast majority of studies analyzed using cause-specific hazard models? Why is that so strongly advocated? And the problem, if you sort of read between the lines, is that this, even though it's an effect, it's an example of what in the causal mediation literature, we would typically call a total effect, in the sense that it captures all the paths, all the mechanisms by which the treatment affects the outcome of interest. And when competing events are intermediate events, this could be a reason that the investigator would not be satisfied with this. So here's just a causal diagram representing an example data generating assumption on the data generating process in this sort of quote perfect trial. So we draw no common causes between A and anything else because of the randomization of A, but of course we can't rule out that there are not common causes of post-randomization treatment processes that we don't directly control. So here we allow, for example, that there are shared common causes of the two different processes, which we just denote by Z. And we also could separate these from unique shared causes of just the, say, prostate cancer death process and the, say, cardiovascular disease process, which we denote by UY and UD. And all of these common causes will come into play in later on. But for now, I just want to focus on these blue arrows, which sort of depict that deterministic defining feature of the competing events data structure, that if D equals 1, then future Y must take the value 0. And when we cannot rule out, based on our working subject matter knowledge, that there are also arrows from A to D nodes that are not intersected by Y, then the total effect is going to capture paths from A to Y that flow through these effectively deterministic blue arrows. And so to bring this back to the example, so estrogen therapy, we reanalyzed this data. Estrogen therapy was found to protect, or we estimate it protects against prostate cancer death on the scale of the total effect. In other words, comparing estimates of the cause-specific cumulative incidence function. So this just shows we did this with a few different estimators. You can ignore that to deal with loss to follow-up, which did not matter in this example. But we see that at least we estimate that consistently over time, the cause-specific cumulative incidence for prostate cancer death is consistently higher under placebo than under treatment. But we find the reverse when we look at the total effect, thinking about the cause-specific cumulative incidence for other deaths, say cardiovascular disease. So we see a reverse of almost in equal magnitude flip of the curves. We see consistently that we estimate the cause-specific cumulative incidence of other death is consistently higher under active treatment. And this raises some questions that would raise some concern when thinking about the underlying subject matter and about potential mechanisms of this treatment. So neither of these total effects allow us to distinguish between any of the following scenarios. They don't tell us whether, say, the protective effect of treatment on prostate cancer death is due only to, say, a desirable action of estrogen that prohibits proliferation of prostate cancer cells, or it could this be due only to an action of estrogen that just kills people off due to heart attacks? We cannot distinguish that based on actually either of those total effects, based on the total effect on prostate cancer death or other death, because total effects do not quantify anything about mechanism. So if the investigators do care about this, the knowledge of the total effects is insufficient. So even though this was a perfect trial and we can estimate a causal effect, this particular causal effect will not allow us to distinguish between these scenarios, and something else will have to be put on top of this to interpret it, even if it's just an assumption about how these treatment works. So I want to clarify this because I've given this talk a number of times and I've learned a lot from the reactions. I'm not giving a recommendation in this talk on what you should estimate. I'm not saying don't estimate the total effect. For example, if you take the perspective that I refuse to try to answer anything that I cannot answer directly from a trial where the assumptions would be guaranteed in the trial that I did. But what I'm saying is that we can't delude ourselves into interpreting it in a different way than we should. So if the investigator is satisfied with the total effect, then you're good. If they're not, then you need to think about something else. And crucially, anything else we consider that would quantify mechanism will not be guaranteed identified, even in this perfect trial. We would have to think about what is the desired target, and like we always have to do in causal inference, reason from that using assumptions encoded in our causal model to claim that we can identify it, and then we can think about statistics. So again, this talk is focused on more the first part of that task. So what are our options then for a measure of direct effect in this case? And what I want to start with is a widely popular measure, probably the most popular measure used in the analysis of competing risk data that I believe is so popular because it is being interpreted as a direct treatment effect that does not capture this, what I've started calling a pathological mediation by competing events, but actually does not meet our definition of a causal effect, and that's the cause-specific hazard ratio. So many authors have strongly advocated for reporting a cause-specific hazard ratio when competing events are present and interest is in, quote, etiology. And the problem is that hazard ratios in general, regardless of whether they're cause-specific or otherwise, are not causal effects, at least in the sense that we define them, meaning contrast and counterfactual outcomes under different treatments, but in the same units, the same population, the same individuals. And even when they contrast counterfactual hazards, additional assumptions are always going to be needed to equate a hazard comparison, even a counterfactual one, to some causal effect. And importantly, these assumptions are generally going to be beyond what we need to actually identify and estimate an actual direct effect, which we haven't even yet defined. So just for those of you who are not that familiar with some of these terms from the competing risk literature, what is a cause-specific hazard ratio or hazard? A cause-specific hazard is just, again, using this more simplistic discrete time event process notation, can just be understood as the probability for, when we say cause-specific, meaning the cause of failure of interest, would just be the probability of failing due to the event of interest by a particular time among those who survived all previous causes of failure, including due to the event of interest and the competing events. So in our example, this would just be those who survive all causes, who are alive up to the previous time. So this does not meet our definition of a causal effect in the sense that a counterfactual contrast in this is comparing counterfactual outcomes under different treatments, A equals 1 versus A equals 0, but in different sets of individuals. So this is those who would survive all causes under treatment And this is those who would survive all causes under placebo. And in general, these will be different groups of people, particularly when treatment has any effect on D or Y. The subdistribution hazard, the other very popular measure that I mentioned, although not as widely used, but widely considered in sort of competing risk textbooks, has the same problem in the sense that, again, this is conditioning on different sets of people, but the subdistribution hazard differs from the cause-specific hazard just in that it's marginal with respect to D. So effectively, this does not actually solve the problem that led us away from the total effect in the first place. So we're just going to move on from this because it doesn't even capture direct effects if that was the goal. So there are, as I said, conditions under which we could equate a cause-specific hazard contrast to a causal effect. One trivial example would again just be under the null. We could just remove the A labels from both sides, and now we are comparing the same populations. Of course, we don't typically fund trials to under the assumption that there's no treatment effect. So this is sort of again, an over trivial type of assumption. Another special case could be if we could measure and adjust for, in this example, all of the common causes on this graph and in some sense condition on them, then a statistic that went after something like that could potentially be given a causal interpretation. But again, the point is that we haven't even yet defined what that interpretation could be and if it's what the investigator would want. And in fact, if we started with a number of candidates for an actual direct effect, none of those candidates would require worrying about those unique event-specific common causes, UY and UD. They would only rely on measuring and adjusting for the shared causes, Z. So we're sort of shooting ourselves in the foot from the beginning if we start with a cause-specific hazard ratio. Again, there may be special cases where that makes sense, but in general, it's better to start with a clear notion of effect. And I just want to point out that a very practical implication of this is just, again, if we're planning a trial and there is a strong possibility that the total effect interpretation may be compromised by this, then it's important to think about what the investigators really do want to know. And that could end up requiring thinking about measuring covariates at the same level that we would have to think about that with an observational study. So if we're not interested in a hazard ratio and we're not we've rejected a total effect, then what are our options with grounding and analysis? And there are a few things that we might look to the causal inference literature to apply to this problem. So for example, what if instead of the total effect, we considered a similar contrast in the probability that Y equals 1 under A equals 1 versus A equals 0, but relative to a world where we could fix the competing event process throughout to just be 0. In other words, eliminate competing events. This turns out to be a special case of the control direct effect, first posed by Robbins and Greenland from the mediation literature. And it also coincides with a counterfactual contrast with that other popular measure that you can find in competing risk textbooks, a marginal cumulative incidence or net risk. And one convenient property of this is that if we started with this target, aside from being meeting our definition of a causal effect and not capturing those undesirable mechanisms, if you will, via competing events, it also will lead us down, if we sort of thought through assumptions, it could lead us down to sort of popular familiar statistics for right sensor data, where effectively we're just treating competing events exactly like we would say loss to follow-up. So that's very appealing. Another sort of popular measure from the mediation literature that maybe we could sort of naively try to apply here might be the natural direct effect, which has indirect analogs. So maybe we could think about a counterfactual contrast under A equals 1 versus A equals 0, but instead of where we fix D bar to be 0, instead we assign the competing event process to be that under placebo. So that would be sort of a direct application of the definition of the natural direct effect, where we think of the mediator, where the D bar process is our time varying mediator. And then finally, we have the survivor average causal effect, which would be another, all three of these share the property that they, again, all meet our definition of a causal effect. All of them would sort of avoid paths from A to Y via D effectively. The survivor average causal effect would refer, though, to a subset of the original population who would never experience the competing event regardless of treatment. So all three of these sort of share the potential issue. If you were to really push an investigator to tell you, why did you design this trial? What are you trying to inform? All of these estimands really don't have a direct translation into the real world. These clearly do not, in the sense that we cannot eliminate death, we cannot directly manipulate competing events. And certainly when we give people A = 1, we don't get to observe what their competing event process would be under A = 0. And this guy here, for example, if A has a very strong effect on D, who are these people? Are they highly unusual? Is this real, or do they even exist? Is this really the group of, were the investigators really only interested in this particular group? So arguably the policy clinical relevance of these targets could be questionable. So now we've sort of led ourselves to a dead end. The investigator tells us, no, now that you've explained to me what the total effect is, I don't want that. Now you've given me all these other potential definitions of direct effect. No, that's not what I wanted. So now what do you do? Well, I think I've come to the conclusion that the investigator has to tell you then what they want. But what leads us to sort of this new class of effects, which we now term the separable effects, really has come out of investigators telling these stories about what they're actually interested in, which is why they may be a useful thing to start thinking about. And the first story, example of this story, is from a chapter by Robbins and Richardson from 2010, where they recounted a story told by Pearl, where he was trying to defend the clinical or actionable relevance of natural effects in a, quote, usual mediation setting. So this was not discussing competing events at all. It was just sort of a, quote, typical mediation problem where the example was interest in the direct and indirect effect, the natural direct and indirect effect of smoking on MI relative to blood pressure. And so to sort of defend the clinical relevance or explain, inform what could be clinically relevant from what we learn about natural effects from a study, he told a story about effects of a modified cigarette, which could be tested in a forearm trial where individuals are not only randomized to the current A = 0 and A = 1, A = 0 being not smoking and A = 1 being smoking current cigarettes, but consider two additional arms where other individuals are randomized to smoke a modified cigarette with just nicotine removed, and then another one with just tobacco removed. And then he went on to tell a very detailed story about the current working assumptions on the mechanisms by which tobacco and nicotine directly and indirectly affect the outcome of interest MI and the intermediate blood pressure, and use that story to give an argument how comparisons of outcomes across these four arms could quantify something that would be meaningfully interpreted as a direct or indirect effect of smoking via blood pressure on MI. But Robbins and Richardson pointed out this is not a story about natural effects. This is a story about a modified treatment effect, a modified version of the original study treatment. And to estimate this type of effect would require a different thought process for identification and to decide how to get to statistics. For example, what types of covariates would need to be adjusted for, and then what would those ultimate statistics look like. And so coming back to competing events, Vanessa de Deleuze extended this idea posed by Robbins and Richardson to the case of survival outcomes with a time varying mediator, which comes very close to where we are now. And Matt Stensrud made this leap to see that, hey, if we thought about this time varying mediator as the D process, which has this very particular deterministic relationship with the outcome, that now we have a new way of thinking about direct and indirect effects for this very relevant mediator, where sometimes it's really hard to ignore interest in mediation. And so there's a number of sort of follow-on results that have come out of this to both allow for a case, for example, on the graph I showed, where there's an arrow from the common cause from A to Z, and giving different ways of interpreting what we now call the separable effects in terms of the mechanisms of A on the event of interest relative to the competing event process. And there are a number of other extensions. For example, what if our outcome, death is sort of a ubiquitous problem, even in non-survival situations, say the outcome is birth weight, and you're studying fertility treatments, and some couples don't conceive or they don't have a live birth. How do you define a causal effect of fertility treatments on birth weight when that outcome is not even defined? And separable effects can be even more central, I think, to that kind of problem. And then we also have some new results on, quote, recurrent events. I don't know how I'm doing on time, but feel free to cut me off. Okay, so like all prior notions of effects that quantify mechanisms that we're sort of used to from the causal inference literature, the control direct effect, natural effects, or even the SACE, separable effects will always rely on stronger assumptions for identification than a total effect. And this is something that's a little hard, I think, particularly for trialists to wrap their heads around, because we're sort of used to relying on the randomization. But again, this is a special case where the total effect may not be enough inherently. And if we decide that, we really do have to think about these necessary additional assumptions and what that implies for even just for covariate collection. But the distinction between the separable effects, I think, and these historical notions is that they can be applied in a much more real world way. And again, they really have naturally come out of, rather than out of sort of a statistician's head, they've come out of very subject matter driven stories about what is actually of interest. And Mats has been doing a nice job collecting up some of those stories. So Pearl did tell that story, but you can find a lot of sort of similar descriptions in discussion sections. And so one thing that sometimes is originally kind of viewed or felt as a limitation is that these explicitly rely on working knowledge of subject matter and very specific stories about mechanism. You sort of saw in that example that Pearl told a very detailed story about how he thinks cigarettes work on the mediator and the outcome. And just stealing a line from Thomas Richardson, I think this should be viewed as a feature, not a bug, of the separable effects, in the sense that it forces to the forefront, even when we're struggling with that story, where there's thinking that remains, which gives a chance for experts to debate and refine stories or disagree with another story and just bring new ideas. And the more clarity that we have on questions that we're motivating our studies with, which require resources, which require risk to patients, we're going to get better answers out of them. So if I still have time, do I still have time? I can go through some of more of the details of separable effects, or I can just kind of jump to some resources.
Yeah, there's at least 6 minutes more. So
okay,
if that's enough.
Yeah, I'll go through the rest of this. So so what are the separable effects? How can we define them? What kind of assumptions would we need to think about here? So the first assumption we have to think about is what we call the modified treatment assumption. And to sort of think about this assumption, it does help to do the thought process that Pearl did, to think about a new study where instead of assigning A, we assign combinations of new treatments. Let's call them A, Y, and AD. And the modified treatment assumption just states that jointly assigning these two new treatments, A, Y, and AD, to the same value A, so assigning A, Y, and AD to 1, leads to exactly the same values of the future event process, and I actually don't have here, including their common causes, had we assigned the original treatment to 1, let's say, or we could replace that with 0. So what this assumption plays 2 roles. We need this assumption for identification, which is what we're sort of used to thinking about assumptions for in causal inference, but we also need this assumption in order to interpret these separable effects, which, as we'll see, are effects of joint interventions on these candidate treatments, A, Y, and AD, as capturing particular mechanisms of the original treatment, A. And this is a strong assumption, there's no doubt, but it could in principle be tested or falsified, say in a future 6-arm trial where you randomize both levels of A and all combinations of A, Y, and AD. A special case where this will hold is when A, Y, and AD are a physical decomposition of A, as in Pearl's story, but as we've written about in some of these papers, this is not a requirement. So not being able to think about a physical decomposition of A does not preclude you from thinking about separable effects. You only need to think about this assumption. So A, Y, and AD could be completely physically separate from A as long as they have this property. So what is a separable effect? We'll define a separable effect of AY evaluated at some level of AD as just really a total effect. So this looks just like the total effect, but instead of having A here, we have combinations of AY and AD. So we compare AY, the outcome Y under AY equals 1 to AY equals 0, holding AD at a fixed level. So there could be 2 separable effects of AY in principle if they're for different levels of AD. And under particular mechanistic assumptions about how these candidate treatments, A, Y, and AD, operate on Y and D, then this could be interpreted as a direct effect of A on the outcome of interest, not through D. And similarly, the separable effect of AD evaluated at a level of AY is just a contrast in the outcomes under AD equals 1 versus AD equals 0, fixing AY. And again, under particular mechanistic assumptions, this could be interpreted as an indirect effect of A on Y only through D. But in fact, we can consider a range of mechanistic assumptions that are analogous to sort of path-specific effects, if some of you are familiar with that, using conditions that a range of from strong to weak isolation conditions that will basically affect the interpretation of these counterfactual contrasts. So just to sort of look at a way to think about this. So here's that original causal diagram that I showed, and I've suppressed the UY and UD because, again, we don't have to worry about those at all anymore for this purpose. They can be there or they cannot be there, but we do have to think about this Z, the shared cause of Y and D. And for now, I'm just going to be even agnostic as to whether it's measured, because I'm not even yet talking about identification. I'm just talking about interpretation of these quantities. So this is an extended causal graph posed by Robbins and Richardson, and it depicts what we call the assumption of full isolation, which is a mechanistic assumption on AY and AD. And basically what this means is that under full isolation, the AY separable effects contain all the direct effects of A on Y, and the AD separable effects contain all the indirect effects of A on Y. And this is, you can see this visually, all the paths from A to Y that flow through AY do not contain D, and all the paths that flow from A to Y through AD are intersected by D. So this is sort of the cleanest case where we can think of these separable effects as direct and indirect effects of A on Y via D, but we can weaken these isolation conditions. So this is an example of partial isolation, what we call partial isolation, and this could come from an original DAG where we allowed an arrow from A to the common cause Z. So for example, depending, and again, this does require some kind of story, and if we have no story, then we're saying this is some candidate treatments that we can't yet articulate, and this is some hypothesis on how those future treatments could work. But this would allow that the AD component affects the common cause Z. So in this example, under partial isolation, the separable AY effect still is a direct effect in the sense that all the paths that flow from A to Y via AY do not contain D, but the AD effects now contain both some of the direct effects and all the indirect effects, because now we see that there are paths from A to Y that flow through AD that also do not contain D. So again, you can see, so Mats is very good at sort of coming up with some of these stories, and we have some in the paper that could even show a clinically relevant story where even in this case, the separable AY effect could be interesting, or even the separable AD effect, maybe a new version of the treatment that reduces some unwanted side effects, let's say. And this is just a bit about identification. So we require, again, the modified treatment assumption is required for interpretation, but also for, not surprisingly, for identification. Here we need all the assumptions that the total effect needed with respect to A, but we'll need some, not surprisingly, some additional independencies to hold, and these will depend on the measured common causes like Z or relevant proxies, and we call these dismissible component conditions. And you can see a number of results and a number of possible statistics that sort of fall out of this in Mats's lifetime data analysis paper. So here are just a number of references. Mats and I have a number of workshops coming up in person and virtually in the next few months that sort of expand on this in like 4 or 5 hours, if this is interesting. And Paloma Rojas Sañero, who's a postdoc at UCLA, has done a really nice job putting together a web page that is really well annotated, that goes through some of the code from these two sort of initial papers that cover a lot of the sort of basic ideas that I covered. And that's it. Thank you.
Thank you so much, Jessica. What a great overview. Mats has heroically answered a lot of questions in a very detailed way. So let's, in the interest of time, move to the discussion right away, and then maybe we'll have some time to discuss after them. Jacqueline, feel free to share.
Great. Okay, can you see my screen?
Yes.
Awesome. Thank you, Jessica, for an excellent talk, and thank you as well to the organizers. In this presentation, I will recap some of the main points of the talk and make some remarks, and I hope that Jessica can help shed light on where my thinking is right and where it might be off. So briefly, some acknowledgements. I have to first thank Dr. Katie Lesko, who was the originally scheduled discussant for this talk, but due to a scheduling conflict, gave me this opportunity to speak today. I also want to acknowledge that I am an epidemiologist by training and not a statistician, and this informs the way I approach competing events as well as all analyses. So as a first remark, I'll start by giving 3 examples of where competing events have come into play in my work, and there will actually be some overlap with examples Jessica gave. And in my experience, competing events are almost ubiquitous in applied analyses, although their degree of relevance or how much they are a nuisance varies from analysis to analysis. So the first example is from an analysis where we aim to estimate the effect of a cancer diagnosis on time to dementia among people with HIV. And of course, we had to recognize that death following cancer and as people age is common. And all-cause mortality and dementia share some common causes like age and comorbidities, but they also have distinct causes. Additionally, we recognize that death prevents dementia, but dementia does not prevent death. And finally, that death can be delayed, but perhaps never eliminated. In our second example, we have competing causes of death, like the example Jessica gave. So in this analysis, we aimed to estimate the effect of medication for opioid use disorder on time to death due to overdose among people who use drugs. And deaths due to other causes like comorbidities prevents death due to overdose and vice versa. And while one can imagine a world in which overdose deaths were eliminated or severely reduced, we likely could again never eliminate all causes of death. And finally, to move on from death as a competing event, we had an analysis where we aimed to estimate the effect of preconception low-dose aspirin on pregnancy outcomes, including live birth and birth weight. And to have a live birth, a woman had to become pregnant. And in a trial where you assign the exposure preconception, it is reasonable to imagine that not all women would become pregnant during the course of follow-up. is additionally unreasonable or unethical to intervene to force all women to become pregnant by the time they were censored. So moving on now to start talking about the points made in Jessica's talk, as well as the contributions of their group's papers to the literature. So to back up again to the classic statistical approaches to, and I put in quotes, account, because this is how it's often phrased without further explanation, for competing events. And those include, as has been mentioned, the cause-specific hazard, which has primarily has been treated as the primary measure of time to event in this setting, the cumulative incidence function, and the subdistribution hazard. And if you peruse this literature, you'll often see debates on whether things like the cause-specific hazard or the subdistribution hazard is more realistic or meaningful, and individuals will often default to either fitting a Cox model or a fine-grained model, especially if they want to control for confounders. And additionally, in the classic stats literature, as Jessica mentioned, when people have been made a recommendation on the statistical estimate to estimate, nearly every teaching paper on competing events makes this distinction that the cause-specific hazard ratio should be estimated for etiology, and contrast of the cumulative incidence function or subdistribution hazard ratio should be estimated for questions of prediction, incidence, or intervention. I've seen it phrased a few ways. And whenever I read this, I always asked, what does this even mean? I have always personally kind of despised this distinction. First, because I think it is unclear what is meant by etiologic. Seemingly, it's about trying to determine some underlying biological effect, or to use the phrasing from Jessica's talk, a mechanistic effect. And while etiologic connotes causal, certainly these authors did not mean causal in a broad sense. And additionally, what is meant by useful for prediction or incidence? And I'd say it's certainly not pure prediction or just description of incidence, neither of which are a causal goal, but perhaps prediction in the sense of counterfactual estimation under hypothetical intervention. It's not entirely clear. And this lack of clarity ties into the second reason, which I think Jessica argues very effectively. It's that this distinction made in the classic statistical literature is not useful because it still focuses on statistical estimands rather than causal estimands. And so it's better to decide on a clearly stated counterfactual estimand that clearly aligns with the goal of the research project, and then consider whether that estimand can be identified and estimated from the data. And so in a sense, rather than perpetuating this debate from the classical statistical literature, we should simply move on and refocus our attention on causal estimates. As a final point, in switching to a more causal framework, what purpose do the classic statistical estimands serve? Well, they are still useful as perhaps nuisance parameters required to estimate the causal estimates of interest, and are thus affected by assumptions related to statistical model specification. All right, so now switching to think about relevant causal estimands, the distinction, I think, as laid out in Jessica's talk, largely becomes about whether we want to estimate a total effect or some kind of direct effect, and which would better answer our research question. Now, total effects estimate the impact of the exposure on the outcome, allowing the competing event to occur as it would under that exposure intervention. Direct effects, on the other hand, I think as has been explained, have a more mechanistic focus, and there are a few choices for the target estimand. So ignoring separable effects for the moment, there's this group of direct effect estimands, which I think, as Jessica argued, are largely impossible or impractical. The controlled direct effect is only realistic if we can prevent the competing event. Natural direct effects require cross-order assumptions. And with the survivor average causal effect, we have this difficulty in determining who our target population is. But suppose these theoretical concerns were not a problem. What would we then want to estimate? Well, this is entirely question dependent, as Jessica discussed. I will say that one thing I personally struggle with, and perhaps this is because of my training, is the practical relevance of estimating direct effects. And this is because the total effect reflects what you would potentially see in the real world under an intervention on the exposure. And the competing event is an inherent characteristic of the system under study, and toggling the exposure could potentially have an impact on the competing event, even if it was not designed to do so. To use a very extreme example, does it matter whether the intervention prevents a dangerous health outcome if it also greatly increased the risk of death in the target population. For this reason, I'd somewhat argue that total effects are more policy relevant and perhaps worthwhile to estimate even in the setting where a mechanistic question is more directly of interest to the content area expert, at least for understanding what is going on with the competing event. But I will point out this is my subjective opinion, and I know many, including many of my colleagues, disagree. So now moving on to talking about separable effects, are these the best alternative to the total effect? Well, I'd say in theory, yes. Interpretation of separable effects is more reasonable than other direct effect estimands. And like the total effect, the intervention is clearer and more realistic. But while these estimands are nice in theory, it's also important to consider how practical they are. So first, let's ask what kinds of interventions can impact the outcome of interest without in some way changing the competing event? And that's a difficult question, and one that will depend greatly on subject matter area and potentially creative thinking. Second, when do we have the data to identify and estimate separable effects? Well, clearly you would have it if you were actually able to design that trial where you looked at the decomposed intervention. In secondary data, which is what I work in most of the time, these effects seem to be able to be modeled even if the decomposition is only hypothetical, but we have to be careful not to stretch the truth too far. As is mentioned in the Stenser 2021 paper, if the decomposed intervention is possible in principle, but perhaps not in practice, we have some difficulty in assessing our identification conditions. Lastly, I'd like to reiterate that the isolation conditions are critical in this when estimating separable effects. And of course, they could be verified empirically if we were to run that trial of the decomposed intervention, but otherwise it joins our list of other untestable identification conditions. My last remark is a brief remark, and one that I think is somewhat taken for granted in this paper is that the important contribution of the Young 2020 paper in establishing DAGs for the competing event setting. So prior to that paper, competing event DAGs were often ad hoc and did not necessarily follow standard DAG rules. And it's important to establish formal DAGs because once those are determined, it is much easier to see our causal structure, think through identification results, and to convey information about our causal estimates and assumptions to colleagues. And these DAGs place the competing event as a mediator, which has important implications for the possible causal estimates as has been laid out, and the identification of this effects. And one thing that I think about when thinking about the competing event as a mediator is the assumption about the timing of the two events this makes, and whether it always makes sense for D or competing event to precede Y. So thank you for giving me the opportunity to discuss. I'll close with this quote from slide 36, which I think is really important. The more clarity we have on the questions we choose to ask, the more clarity we have in how best to answer them. Thank you.
Thanks so much, Jacqueline. Very nice discussion. So maybe we could take just a few minutes to kind of reflect on Jacqueline's points. Jessica or Mats, if you would like, and then we'll wrap up.
Yeah, thank you so much, Jackie. That was really nice. And it's nice to sort of hear about different applications that you've dealt with. So I have to remember all of the questions. I think just the last one you mentioned about the time ordering. So I think that really, that is really just a feature of sort of our need to sort of discretize time in our brains. But if we started thinking about the real causal diagram, the real event process, the real data generating process, we could think of these time jumps in seconds. And once we start doing that, basically, we don't really have to worry about the time ordering anymore, because within a particular second, we're not going to have to worry, for example, about common causes, or the chance of more than one event becomes zero, and we can sort of search. That will we could start to see. That's why I think on this graph, I've tried to get into the habit to not put the same time index on the DAG. So that's why I have D1, Y2, D3, because that can be very confusing to put an arrow from D1 into Y1, for example. And really that time ordering is really just a result of over coarsening often of the data that we usually have. I don't know if that's a very satisfying answer.
You can make a comparative answer. Sorry for chiming in, but
no, please.
In any continuous time survival analysis, if you have ties in the data, first of all, that violates the assumption that the survival times are absolutely continuous, because then you can't have ties. So somehow that model is violated. The other thing is, what do they do in practice? They do a random draw whether one of the event before the other, or they consider them to be at the same time. So the ordering that Y is after D is totally arbitrary. Simple sensitivity analysis is just to change the order and do exactly the same thing, essentially, and see if it matters. And if you discretize time in a grid that's fine enough, it wouldn't matter. Jessica said.
Yeah, but that gets very hard. So I think that also gets to what you were saying about how hard it is to think about the separable effects, and that total effects are probably the most policy relevant, appealing answer. And I actually agree, and sort of in practice, I work with a lot of implied data analysis, and total effects are always my go-to for this problem, and actually are probably what I have been prioritizing in actual survival analysis type problems, because the total effects are defined in that case. And so I think then on top, everything else we think about beyond that, I think it's useful to think about these other things as kind of as a follow-on to the total effect. So just to give you one example, we worked on a study of PrEP uptake and HIV, pre-exposure prophylaxis for HIV, and HIV is the outcome. And there are some deaths in the data. And this was sort of a relatively short follow-up period, where basically you can make an argument that if I were drawing this DAG, the bottom line is, in that study, it was reasonable to not draw arrows on the DAG from A into the D nodes, not intersected by Y. So that's a case where the total effect can be interpreted as a direct effect. And what I've done is I've augmented my analysis with a story about mechanism. And I feel so confident about that I'm not going to bother to do a follow-on analysis, because I don't feel that my interpretation of the total effect is compromised by this problem, or the investigators I was working with did not. But it's really only when the investigator says, no, this is not satisfactory to me. And as you said, when you talk to your colleagues, different people will give you different answers. And I think that's a reality that we have to contend with, and we have to, I used to take more of a view of, this is what I think the right question is, I think, when presenting this. And I think I've learned over time that it's actually not my role to sort of generically say what the right question is, because I'm not a subject matter expert. So it's really up to subject matter experts, and particularly the communities that subject matter is going to affect, that should be having a conversation about what are the important questions, because there are practical resources. There's money that goes into deciding which trials get funded, which interventions get funded. And I think if we're not transparent about what we're actually answering, that process is almost somewhat dishonest. So, yeah.
Thank you all.
That is an excellent point.
Thanks, Jacqueline. Thank you all. Sorry to interrupt you. We're over time, so I'll just wrap up. Apologies. Okay. All right. So just to thank again, actually, Jessica and Jacqueline and Mats for giving great talks and answering a lot of questions. For people whose questions haven't been fully answered to their satisfaction, just know that we will pass on all of your questions to the speakers, and you can then contact them for a follow-up if you're interested. Thank you again all for answering a lot of questions, actually, and having a nice discussion. Next week, we have a talk by Robin Evans from University of Oxford. I hope you all join us for that. And thank you for coming today.